So I have two ways of just trying to figure out how to set up networks. They came up with a method where we can have a physical, so a network adapter. You used to have adapters, now it's all integrated inside your computer. So they came up with a physical address for the network interface circuit. It's called a media access control address. Or a MAC address. And it's a 48-bit binary number. Yeah, that'll have a lot. And basically, the first 24 bits, or the most significant 24 bits, this is a manufacturer's code. That's assigned to a company by, I can't remember who it is. And then this is the most significant bits. And then the least significant bits, 24. This is the actual adapter's address, or the network circuit address.
You don't have that.
Yeah. So this is network electronics. So this is unique. This is like your address at your house or your phone number. Your phone number is unique to you. I don't know what's popping over there. My words are popping over there. This is a network electronics. So that's 48 bits. So that's 2 to the 24th different addresses a manufacturer can assign to these adapters and stuff when they sell them. And then if they run out of that, then they add another manufacturer's code. So that means we could have 2 to the 48th network adapters out there. Now currently, where that's no problem because that's a lot of them. But eventually they'll run out of these, and I don't know what they'll do. So they came up with a method where we could set up where we wouldn't have to broadcast our MAC address out on. They came up with something they called an IP address for Internet Protocol. I don't know what it was doing. It was shifting everything. So an IP address is a 32-bit number, but they understood that it was impossible for humans to understand numbers. So what your computer does is it displays it in decimal. And it comes up and it'll be like 192.168.5.10. Now, the biggest, since it's 8 bits, the biggest number you could have there would be 255. So you'll never see an IP, any of the 4 digits in their numbers over 255. And that's a lot of IP addresses. That's 2 to the 32nd, which was 2 to the 32nd.
Big number.
A big number. And they originally thought it was big enough that we would never need any more. So they gave some of them away. Some of them are assigned specifically to the government. Some assigned for troubleshooting. Some of them is assigned to the internet.
My modem has those numbers.
Yeah, that's the IP address. So, and you have to get one before you can get on a network that uses what we call a TCP/IP network, which is what the internet is. And this is the way we do things now. So originally we had Novell was fighting. They had a protocol called IPX, SPX. Windows, which is still available, it had a protocol called NetBEUI, which is still we still use that on a network that's got a lot of computers running Windows, and then TCP/IP, which is the predominant protocol for sending stuff on the network. TCP is how they put the packets together. It's called Transfer Control Protocol. So we send information in packets. So if you got 1 million bytes of information to send, you don't get access to the network to send 1 million bytes. You send one packet, and then you come off the network and leave it open for other computers to use it. And the way the packets are put together, that's defined by the TCP, and then IP gets out the address. So what happened though, now how many devices at your house needs an IP address? Your phone needs one, your computers need one, everything basically. If you can get on the internet, it requires an IP address. So each one of us probably got 5 or 6 devices that need an IP address. Used to, you had a computer at your house, right? You understand? So what they did, this became known as IPv4, and now they have an IPv6, which is used by the internet, which you don't see. This is a 148-bit address gateway. And what we did a long time ago is they said, okay, we don't need to assign everybody an address to get out on the internet. So you got some addresses that's valid on the internet, and then we have what we call private IPs. These never get out on the internet. So 192.168.5.10, I can use it at Lawson, I could use it at Intel, I could use it just about all over the place because these are private IPs. And then the college, I think, has 2 internet IPs. So when you leave here, you go through this thing called a gateway. It converts my private IP over to the internet IP, which is 140.
Now, is this traceable?
Well, they can trace it back to your router. They can tell where so we are assigned an internet IP. And that IP is attached to inside the TCP packet when it goes out. Because if it didn't attach it to the packet, it wouldn't know where to do what? Come back. Yeah, well, it wouldn't even know how to come back. Because all that information is kept by all these routers and everything that passes this guy through. So yeah, the destination IP and now the MAC address is blocked. Your MAC address does not go out. So they don't know basically which computer inside Lawson's seeing it. They just know it came from Lawson, right?
So what's the purpose of private IPs?
Private IPs allows us, number one, it allows us to duplicate IP addresses because those are kept within the private network, number one, right? You understand? And basically, they never go out. Your router will not pass an IP. Your gateway will not pass a private IP. So it would be like the 7-digit phone numbers right now. So originally we had 7-digit phone. Well, it's actually less than that. 7-digit phone numbers. And of course, what was happening is they were running out of what? Numbers. So what we did is now we come inside the college. So inside the college, I have an office number, right? You understand? Which would be so it's 3439. How many 3439 phones can be out there? A lot of them, because this is not passed through what? Through the switch gear in our phone system. So what it did, it helped a lot when we got inside here, where we could have phone numbers that are not passed through. And then when it comes to our switch station, it decides it strips off the 929 and then passes it through our voice over IP. So 192, I could send you the range. So 192 is private IP. So if you ever look at your IP address, if you got a router at home, it's going to be like a 192 or something like that because that's a private IP. That didn't go out the internet. So we got two ways we can set this up. Well, we can set this up as what we call dynamic IPs. This is assigned by this is not going to be a test, guys. This is just nice because I'm trying to show y'all. So I forgot my cable, my DH45 cable, 485 cable. So I'm having to hook this up. I'm trying to hook this up with this guy's also got Ethernet IP. So dynamic IPs, what happens if you have your computer set up for dynamic IPs? When your computer comes online, your network card comes out, and it asks for a DHCP server, which is Dynamic Host Configuration Protocol. And this is set up by the DHCP server. And in that server, you broadcast out a packet saying, hey, I need an IP address, and then the DHCP server assigns you one. That's free. So we run a DHCP server, even our domain server's got a DHCP server. And I can set up a range of IP addresses I assign. And what's nice about dynamic IPs is I can log off. So you can log into on the internet from your service provider. You can come off. You can turn your computer off, and the next time you come on, you'll have a different IP address. Or you can set up what we call a reservation, where so like ours is set up. So if you turn your computer on, but you turn it back on within 5 days, you get the same IP. Or you can set it up for what we call static IP. Static IPs, you assign the IP. So whoever's controlling your network has to make sure that you have no IP addresses that conflict with each other. So like domain servers, you don't want those suckers to move around. So a server will be assigned a static IP, and then your other computers usually use dynamic IP. Okay. But this is the way we address the computer. So this guy right here, you can't set this for static IPs. The only thing you can set it for is dynamic IPs. So I've got this hooked into my computer. So how do I get the IP in there? Well, what RSLogix 500 provides with their software is it supplies a DHCP toolbar. So when I start this thing up, it's going to start displaying. Oh, because it's already running. Sorry. It starts displaying MAC addresses. So these are MAC addresses. These are physical addresses, guys. And what they do to make it easier, they don't display it in binary, they display it in hexadecimal. And then they split the MAC address up into using colons or dots. So what I needed to do is find out the MAC address for this PLC.
Now what that means?
It's medium access control. That is the physical address that's assigned to that network circuitry when you buy it. So your phone has a MAC address. How did it get in there? Well, when Apple built this phone, or when whoever built your phone, they put that into the circuitry of your phone. And that's a physical address. That never was. You can change your phone number, but you can't change your MAC. Right? Medium access control, yeah. And there's hopefully y'all can see this with my camera. So on this guy, so if you've got a PLC, and this is very, very popular now, one of the first things you're going to have to do before you communicate with it is assign it an IP address. But to assign it an IP address, you got to know the what? Starts with M. So I need to fix it. Let's see if I can do this without shaking so much. Now I've done this so many times, I know the manufacturer's codes for Rowell and Bradley PLCs. So on these guys, I hit escape, and then I'm gonna go down and go to advanced settings. And then I'm gonna go down to Ethernet IP. And here's my MAC address right here. MAC 000F, and that's all we need to know. And this is the IP because I've already done this to assign it. And then what I have to do is I wait for that MAC address to pop up in this application. And then I double click on it, pops down here, I put the what? I put the IP. Now you have to put it in the same subnet, which I'm not going to explain. So there's an application on your computer called ipconfig. And it gives you all the IP addresses of all the devices in your computer. So 192.168.0.100. I have to use for my PLC. I have to use 192.168.0, and then I assigned it another address. You can see which that's what I assigned. Okay. We're still not through. Now, if I was to do this with the DH45, I've only got one device hooked in here. I don't have to do all this stuff, but since I don't have my cables. So what I got to do now is I got to load the driver. What's the driver? Controls the device, right? So what we've done is we just switched over to Ethernet. So I got to load the driver for Ethernet. And hopefully this works, guys. Sometimes it don't. So I'm going to go to communications. I'm going to go to configure driver. And then I'm going to add a protocol. Which ones do we need to add? Ethernet IP, right? Then we have to select the adapter that we're going to go through. So I have to know where my adapter is at on my computer. And there it found the PLC. So we're okay. Are we okay? So that's a lot to it, and even RS Logic 5000 does the same way. So every PLC that's got multiple ways that you can connect to it, one of the first things you have to do, or not, I'm sorry, before you download a program to the PLC, you have to configure that interface between the computer and the PLC. You can write the programs without knowing that, without doing that, but you won't be able to do what? You won't be able to download or upload to the PLC unless you can do that. So lab 6, what is lab 6? We started into this. Not lab 6, chapter 6. Huh?
We jumped chapter 5.
Well, we'll come back and pick up those. What we're trying to do is get into a chapter where y'all can start programming the PLC a little bit instead of actually sitting in here and listening to these lectures. Wouldn't y'all like to do that?
Yeah. So it's basic PLC coming, the data file.
Yeah. And most of it we've already talked about. Some of it, let's rephrase that. Some of it we've already talked about. So let me go ahead and bring up RS Logic. By the way, we've supposedly we pinned it. I don't know if y'all can see it or not. It's a little step ladder down there representing ladder. I think we've got it pinned to the taskbar on all the computers down there. But if we don't, you can go to programs, and then it's inside the group for RS Logics. I'm sorry, Rockwell software, and then it's the RS Logic 500 English. That's the one we're doing. If it's not pinned to your start menu. So we'll go ahead and start it up.
We're going to chapter 6.
Right. So what I just did is I came in here to download the program. I went to comms, and I went to system communication, and then I found my PLC that I want to communicate. Now, if we had these guys networked together, then every PLC on the network would be in this list. In fact, we could have two groups. We could have one using the DHCP. Of course, it says I don't have that connected. That's what the X means. And you can be running several communication protocols on your computer at the same time to connect to different PLCs that use this. So I'm ready. So what is chapter 6? Yep. This is not in your textbook. We actually have at least 5 different languages we can program the PLC. We have what we call structured text. What they were trying to do is they were trying to teach a method where people that came up through different disciplines would have the ability to program the PLC without having to learn a different language, a programming language. Of course, the language that we're going to look at is ladder, but I just wanted to show you this. So this is a language we call structured text. It's very similar to the programming language called C and Pascal, which is a very, very popular programming language for people that's in computer science. So what it did, it gave them a method that people that came up through computers could do what? They could program PLC and pick up on this language very, very easily. Yeah, this is actually for a little microcontroller called an Arduino. This is called function block programming. This was developed for people that came up through electronics or digital. These uses a lot of the logic symbols that we use, like for AND operations, OR operations, greater than or equal to, and set and reset. So here we use symbols to program the PLC. This would be what a person that came up through electronics came through. That had a lot of digital experience. This is called sequential function chart. For years, what they did when we this is flow charting, guys. If you ever started working with computers in the early stages, getting a program on a computer was so complex that we wanted to make sure the program would work or it would flow before we even started writing. So one of the first things that we developed was flow charts, which we had different symbols and stuff that we used. And if it didn't flow in that flow chart, it means what? It wouldn't work in the program, right? So sequential function charts, this is available for people that understand flow charting. Siemens really pushes this, by the way. This is called instruction list. This is very similar to people that learn machine language programming. One step above machine language programming was a programming language called assembly language, which we had to learn all of these, we call them mnemonics, but these are memory joggers. And then you use those instead of using, and what they have over here on the left is actually the ladder logic program that this code right here represents. So this was fun. And then of course what we have now is what? This is what we teach in this class. This is still the predominant programming language because it's understood by, it's easy to pick up on, and also it's understood by multiple threads. So we have two rails on each side. We generically refer to them as what? L1, L2. And then we draw circuits between L1 and L2. And these individual circuits we call what? Runs. And we put inputs on the left, but these are programming. By the programming, when you write programs, each step in a program, we call this an instruction. So all these are instructions. But in ladder logic, we use symbols for instructions. So this instruction right here, we call this an examine if open, examine if closed. And then these are output energized. We pick up that term because that's what we used to say about a relay when we change the position of the contacts with the magnetic. We call it energizing the relay. And this is pretty similar on just about all PLCs that use ladder logic. Sometimes they change the symbol a little bit. But RS Logic 500 uses that guy for output. This is the rules for creating PLC ladder diagrams. Of course, we've already gave that out, right? We gave everybody a copy of that, right? Convert a relay logic diagram to a PLC ladder diagram. Create. These are the first labs we're going to do, by the way. And then as we move forward, sooner or later, you're going to have to create it from a list that tells you what the program is supposed to do. Create logic diagrams using PLC in the offline mode. Download PLC ladder logic diagrams and test them on a trainer, which is what you're going to do, right? We're going to play around with the force instruction, which allows us to literally force these devices into another state. Create a print program. We're not going to do that. We are going to save an open ladder diagram project file. Okay? Okay, so to create a relay logic diagram, use the inputs, the device symbols. So, and we're still going to have to learn these. There's very few symbols in the PLC that we'll use this semester. But these are the actual symbols that would be used in a relay logic. And of course, this guy drew it wrong. In electricity, we should put dots anytime we have a connection. So what's this symbol for? Well, you got to look real careful. This guy didn't draw it right. If it's above, so he should have put a bunch of space there. If the push button is above, it's normally open. If it's a below and it's got to touch the dots, this is normally closed. So notice these are above. It's just really hard to see what the space. This guy is really close. Huh? It's there, yeah. So these are push buttons.
They're
So
circles supposed to be shaped in.
no, they're not.
I'm saying if it's connected or closed.
No, these are supposed to be left open. This indicates a connection. This indicates a terminal that we connect to. So these are supposed to be drawn open. You'll see them drawn in sometimes. These are supposed to be open because this is not a permanent connection. So the dot is a permanent connection dot, a point. The not shaded in circle is a temporary connection. But you see a lot of people not draw that right. And as long as you understand, it's no big deal, right? So this is a push button. And it's usually not momentary contact.
What about a normal flow, whatever we say?
What do you mean?
Normal flow.
Because it's a temporary connection. I can break it just by pushing down on it, right? That makes sense. This is a permanent connection point. This is not a permanent connection. It is not. If it was permanently connected, it wouldn't be a switch, it would be a what? It'd be a piece of wire, and we wouldn't have the dot there in the first place. This is a limit switch, normally open. Don't know what a limit switch is. Everybody okay? We got one on the table over here we can hand out. These are mechanically operated by somebody, by the people, right? And this is a relay coil. Not a motor. Coil, a coil that controls contacts. We just don't show the contacts that it controls. So if I was going to come down here and show y'all what was going on, I would come over here and I would we put a dot, and I put a normally open contact. I give it exactly the same name as the relay that controls it. And then I would come over here and I would put an output. And that's not a reindeer. That's a light. I get down close to that. So what we need to understand is that we need to. So what we're going to do is we're going to connect switches to the PLC. We know that each one of these is called what? Are we okay? And PLC, we would take this same circuit and we would represent it by instruction. So this is an examine if closed. We have two of those in here. There's an examine if closed instruction. And this is an output energize instruction. This makes sense. And then what we have to do is we give it an address that tells the PLC the location of the terminal that this switch is going to be connected to. It does. We can't. The only motors that we put inside this guy, inside the control circuit, is maybe a little tiny fan motor. We probably normally when we run controls, we very seldom run motors directly in the control circuit. In fact, all the PLCs that we've got here So normally a control circuit is set up on two sections. If we have a control circuit that uses low voltage, some of the things this guy does, I'm not really impressed by. And then we have a power circuit. And this is going to be high voltage. And then what we'll do is over here, we'll have a relay over here, maybe called M1. And then my control circuit would energize the coil from here. And over here, we might have 26 volts or 24 volts if it's DC. And over here, we might have, what's the highest voltage y'all have it?
120,
In your control circuit at y'all's plant?
Oh, it's fine.
Yeah, at the plant.
I like 50,000.
Probably not. Yeah, the highest voltage US Steel had was 660. I mean 6,660. Was it 480?
What voltage is it?
Just about all of them have 480. And this is what all your motors run off of, right? You don't have any motors inside your control cabinet. And you got two cabinets out there. You got one that's got the control, and you got one that's got the high voltage stuff. And then you have wires running from the control cabinet over to the high powered stuff. But this is like 24 volts DC. So, and then you'll have, that would be where your PLC is, or that makes sense. And why? Why do we want our control to be low voltage, John? Because the lower the voltage, what's the advantage of low voltage over high voltage? Yeah, safety. What advantage does high voltage have over low voltage?
Can't run a condenser motor.
Why? Well, you could if it was a small condenser.
Well,
So if you had a little portable.
I'm thinking about an air conditioner. I just did that.
But you're right. It has a lot to do with the cost, because what we can do is we can use smaller components. Because the higher the voltage, the less current required to produce the power, right? So we can use smaller conductors. We can use smaller size relays. We can use smaller coils that actually energize them. It don't save money on running them, because we don't pay for voltage and we don't pay for current. What do we pay for? So that could be a motor. If it was a motor, it would be a little old tiny motor. It wouldn't be a big motor. It might be a fan motor or something like that. It definitely wouldn't be a motor that's running a condenser. Yeah. But they're very, very small. So if the book says it's a motor, we can leave it a motor. Just the motor won't have what? The motor won't have what? You're right. A motor won't have contacts. But over here, we're not going to hook the motor inside the PLC, so I guess it's pretty good. What we're going to do is we're going to generate an output, and then we're going to specify an output terminal. Are we okay? Okay, so let's say this is input 0/0, and then I have another terminal, which should be input, 0/1, then I have another terminal, input 0/2, and that's all we're using, right? And over here on my PLC, I would have one kind of label like this, output 0/0. Now over here, this is where we're going to hook our switches. So I come over here, and we have two normally open switches, or push buttons, excuse me. And then we have a normally open. So what do I need? I need some type of circuit, right? Is this a circuit? Okay, what do we need? We need a source. So we have to establish a common. So this is what we have to talk about on our book. So we'll have one of the leads up here. It's going to be terminal called common. Makes sense so far. So what I've done is I've set my inputs up to sync. So my devices are what? Now over on my output, this is where the actual little motor would be installed. Glad y'all thinking, guys. So we'll come over here and we'll take this motor. We very seldom hook a motor directly up to a PLC, but we'll do this. And I'm going the wrong way with this because my common's at the top. Now this is where our PLC is going to be different. So I forgot my motor. Just a little thing. So the 1100 does this. And what's that a symbol for? An AC source. Right? Yeah, I wrote motor under that. Because M is a designator that we usually use for a motor starter, so I'm going to try to. Because we very seldom have literally motors inside. Okay. Now this would be for the what? The Micrologic 1000s. So that's the little briefcase PLCs. And then for the 1100s, we have this. So here we're setting the PLC up, the output ports to the stores, and the output devices are going to. Are we okay so far? Okay. Any questions? So let's do this. So I'm going to come over here and go back to RS Logics. It's running. I'm going to do what? First thing I need to do, I'm going to create a new, I'm going to come up here and say what? Yeah, say new first. As soon as I say new, what's the second thing it's going to ask? It's going to ask me to say I got 1100, Micrologic 1100B, which is this big area right there. Look right past it. So here's the actual model number, but this is so this is the guy we got. Okay. B, yeah.
So all of them.
Yeah, all ours are Bs. All our 1100s are Bs. Okay, so what do I need to do next? We can't put anything inside the end rung.
Yeah.
So here's add a rung, right? That's not going to insert me. All right, then what do I do? Bring out a contact. Oops. Then what do we need to do? Yeah, not an IP address. 0/0. And then we need to give it a symbol. Y'all need to start doing this. We'll call this SW1. And then I need a what? Another contact. N:0/1. And the third contact, or input. This is this is third input. This is input : read. You'll see what I did? I used the O instead of a 2.
Oh,
Yeah,
what's
that's,
the limits?
yeah, that's, by the way, what I did for some reason, it didn't take my symbol, so I'm gonna right click down here, and I'm gonna go edit symbol. Why are you taking? It's supposed to be I for input. 0 is the address. 0 is the address for which. 2. Oh, I know what I'm doing. Duh. I'm trying to give it the same. I'm trying to give it the same symbol. Okay. And what's that? Then we put an output energize instruction, and then we assign it to an output port. We're okay so far. And that's our first program. Well, it's not. We've already did. And what would be next? Now notice to write the program, your application has to be offline. RSLogic 500, you cannot modify or change the program with RSLogic being connected to the PLC. That makes sense? So, and to download it, you'll have to be offline. The PLC has to be in the program mode, and we'll talk about that in a minute. But this guy is switched automatically. A lot of your PLCs will have a key on the front of it, which is good because you can put it on run mode, and then you can take the key out, and nobody can do what? They can change it. They can't change the program without having the what? The key in. So a lot of your smaller PLCs don't have that feature. But you can, there's another feature we'll show y'all where you can password protect. I don't know if I'll show you that or not, because as sure as I do it, somebody's going to lie. Password. Yeah, so you can password protect the PLC, and then you can't change it. You can't change the program unless you know what. Huh? I don't know. I wouldn't forget it. Because you can't send an email saying I need to reset my password. So what I do is I put all mine in my phone, and my phone uses biometrics. Anybody got the phone that has facial recognition? That's cool. Okay. So we went from ladder diagram over to what? PLC program, right? All the input devices must be placed horizontally. You don't have to worry about this. This is what? Automatic. Output instructions cannot be connected in series with other output instructions. You won't be able to clear the error. You'll always have an error, right? Understand that? Program execution flow is from left to right. We don't want to create a backflow. The backflow would be, notice here, why they did this or not, I don't know what the purpose of this instruction is right here, because it basically eliminates everything. But it says I gotta have 3 energized to energize this, but it says if 3 are energized, we bypass 1 and 4. So undoubtedly this guy wasn't thinking about that. But notice what happens if I energize 0, which is required by both of them. I energize 1, and then 3 energizes, then we have a backflow back towards L1, and then we can come back this way. So we don't want any backflows like that. Place rung numbers on the left side of the network. Y'all notice this was what? This is automatic on RSLogic 500.
Where's the room?
It's not on here.
Okay. Well, I was cleaning my glasses.
This is not ours. This is the guy's drawing. Here's RSLogic 500, and here's a rung number.
Okay.
So RSLogic 500, the first rung would always be 0. So if I insert a rung above it, then this would become rung 1, and then the other one would become. Let's do that. So to insert a rung, you highlight this. You highlight where you want to put it at. So right now we can put it above 0, or we can put it above 1. So if I insert it right here, or I can come up here and insert it right here. Oops, it didn't do it. And it automatically shifts the numbers. So you wouldn't look at the rung numbers until you finished your project, because the rung numbers are going to do what? They're going to change depending on where you insert the rung at. If you want to delete a rung, you just highlight it and hit the delete key on your keyboard, and it's gone. Everybody okay? If you change it, or a rung is no longer valid, or you decided to put it somewhere else, and I'll show y'all some neat stuff as we move through the class. You can copy and paste, by the way. On relays, the number of contacts and even on switches, the number of contacts you have available on a mechanical switch is going to be limited. On PLCs, it don't care. So on PLCs, we can do neat stuff that would be really hard to do in controls. Is if I want to move this contact, I can grab it and just, I don't know how to move, right? We can cut and paste. We can copy. We can use the shortcut key for copy. I can change the way they're arranged. So if I wanted to put one, I didn't want to do it. Usually you need to grab down here at the bottom. So y'all know how to, right, hold the left mouse button and move it where you want to. If I was to do that on relay logic, I would be moving wires. Here we're not moving wires. I can use this contact over here hundreds of times. Now what's neat about doing a symbol is once I assign it a symbol name, I don't have to even know the address anymore. I can just come in here and type in the symbol, and it automatically puts the address information in. And how many times can I reuse switch 1? Right?
But it's the same address.
It's the same address. But if this was a push button, I'm using it, I want it to be the same address. So a lot of times we want to use the same push button in multiple rungs, right? You understand? It's real hard to in motor controls, because your switches only have so many contacts. You can't have 100 contacts on a manually operated switch. The PLCs don't care. And ladder logic don't care. This is where we check for errors. So as soon as I created a rung, it gave me an error. This guy doesn't clear instantly, so we can use this guy right here. And it says this rung doesn't have an error, and it says this rung has an error. And it tells me file 2, rung 1, it's missing a what? Missing an output, which helps us a lot. Run comments, we place run comments, they go on the top of the device. We can give a run a comment, I'll show y'all that, or we can give a device a comment. The more comments or more information you put above each instruction, the easier it makes for you to remember what you were doing when you come back to your later. Or if some other tech's gotta come in there and take care of your work. We had a guy that was an engineer out at US Steel. His name was Dan Steele. He was a really and they let him come into one of the lines over in the tin mill and make a bunch of modifications. He designed a bunch of circuits and put them in there and didn't teach anybody how they worked and didn't give anybody schematics. Dan retired and became a consultant.
Well, that's smart, right there.
Well, it is, but US Steel shouldn't let him get by with it in the first place.
But they had to pay him to redo all that.
So yeah, they had not to redo it, to come out there and fix it when it broke. Well, he wasn't, but his bosses were dumb for not doing what?
Yeah.
I mean, everything that US Steel bid out, they required all the documentation. So we wouldn't buy any equipment without the diagrams on it. But they let Dan get by with it.
Dan pretty smart.
Dan was pretty smart. He was up there. We had some really smart people out there. Symbols. This is what we're going to require. So symbols are not covered in the textbook. With RS Logic 500, a symbol is an optional logical text address assigned to an input or output instruction's physical address. And what's nice is once you give it this name, you don't have to remember the physical address. You just got to remember the name. Once a symbol has been assigned, the symbol name can be used instead of a physical address. In your PLC application, these are referred to as tags, and they are required. You can understand. It keeps you from duplicating addresses. There's a lot of features on there. For this reason, symbols are required in this class. So what I'm saying is every time you put in an instruction, you're going to do what? You're going to assign it a what? Something. And this will get you prepared when you move into RS Logic 5000 or when you move into or move into one of the Siemens products. Those are all tag. Those are tag-based programming applications. Are we okay? After constructing the relay logic, assigning addresses, connecting input devices to a PLC, and creating PLC logic. Normally we don't do the motor control circuit anymore. Usually now when we program directly into the PLC. We might draw it out. We might set up a plan. We might set up a function chart or a flow chart to make it sure that it works. But I've never seen anybody. When we originally got into PLCs, all our diagrams were relay logic. So that was one of the big things, was converting the relay logic diagram over to PLC. Program application in offline mode, right? Everybody okay with that? While ladder diagram is created, offline mode. This is where, I don't know why this is why. This is where we create the ladder logic. So here's the procedure. This is not a textbook either. If you plan to download the program to the PLC, establish communication with the PLC. Note that the programs can be created without the PLC being connected to the computer. So if you've got the application on your computer, you can create the programs at home. Place RS Logic 500. This is what I was demonstrating right at first, since I was establishing communication with the PLC, right? So I could do what? So I could download and upload the Place RS Logic in 500 in offline mode. Create the new program. Select the CPU for the PLC being programmed. Insert a run before the end instruction. Insert your instructions into the created run. And then we can add additional runs as needed, right? Everybody okay there? I think we've done that a few times in this class. So programming ladder logic, we understand examine if open and examine if closed, right? These are instructions. And then output energized. We're okay there? This is kind of out of whack and select the CPU. So this guy is using a 503. Which is a modular PLC. So we have some 504s down there, and the book deals with the 500 series, and this is a little problem we're having with the book, is that it's written around a specific trainer, and we are not using the trainer anymore. In fact, it's not even written around the trainer that we use. The trainer that the book is written around has 120 volt DC inputs, and we don't have that. So, but this is nice to know for tests. So modular PLCs, what's in slot 0? Yeah, this is where the CPU module resides. Slot 1 is your first module. Of course, this says that it houses a 16-port, 24 volt DC second input module. But that might not be true. What's going to be in slot 1 is what your company bought to put in slot 1. Right? You understand that? And what's going to be in slot 2? The module your company bought to put in slot 2. So this is a problem in that the textbook is written around a specific trainer. But these are modules. Slot 0, CPU. Slot 1, 2, 3, 4, 5, 6, 7, which is what this is a 7-slot rack. This is a 7-slot rack. So what's going to be in slot 1, 2, 3, 4? Slot 1, 2, 3, 4, 5, and 6. Whatever your company bought to put in there, right? So I need to change this slide. This right here is garbage. If you're writing this down, this is not going to be on the test. This is not going to be on the test. That right there is going to be on the test.
Oh, okay.
What's going to be in slot 1? What's going to be in slot 2? So on ours, we have a 16-bit input syncing module on the input, and we have a 16-bit sourcing module on the output for these guys. On this 504, that the school bought. It's not on any 504, it's on this 504. Understand? So when the school bought that 504,
you told them what to buy, didn't you?
no, these guys were bought before Rich started teaching PLC. It was a good trainer, but, and it's good to show and tell. It's just that communication speed, in every lab that we do in this class, we could do on that guy. It's just that the communication speed, it's using that when the ORS2, it's 9,600 bits per second. So when we put our PLC in monitor mode, you flip a switch and the screen won't change colors for about 2 seconds. And then it'll change color. So you're trying to run a counter and you're sitting there waiting on the thing to change and your counter's responding. You're waiting on your counter to update and it's not updating because it is updating, but it's updating in the CPU. It just takes so long for it to what? Send that back to your computer.
But in its study, it's
Yeah. And if you look at an Allen Bradley modular PLC, it's still very similar to that guy right there. It's just that they use a more up-to-date PLC and a faster communication channel. Yeah, this guy right here is 100 megabits. So this right here would respond instantly, right? I think the 485 is 19.2 kilobits, but it's still, and you're the only one communicating over a smaller cable, so it's going to update instantly for you, right? So I think I made a change on this a little bit on the market. I think this book shows 120 volts. I think one of you shows, y'all show 120 volt on y'all's book. There's a figure in there. Yeah, we don't have 120 volts. Kill people. We'll be hauling food out. So we're using, like I said, on 1100s, we're using, what's the voltage on 1100s? Yeah. 24 volts DC. And over here, this is 24 volts too. No, what they've done, of course, is over time, originally they did, and used to, we were controlled, the devices wasn't as efficient as they are now and everything, so 120 volts was very standard in a control circuit. But then we came out with this National Fire Protection, 70E. Have you heard of that? Most people call it 70E. And what did they do that hadn't been done? Well, what they did is they set up safety rules for use. So the 70, the NAFTA 70, which is the National Electrical Code, that is a code that's in there to protect equipment. It's not to protect you. Now, normally, if you install the equipment correctly, it's going to be safely installed, right? You understand? Well, they realized they did not have a standard that did protect the person that was working on that. And they established 50 volts is anything above 50 volts and above is lethal. Anything below that is not lethal. That's what 70 is established. So if you're working at a plant and you get into a control cabinet and it's above 50 volts, you got to start adding to your PPE. Right? What does PPE stand for? Anything below 50 volts is just standard stuff. You know, hard hats maybe, safety glasses, yes, leather shoes probably. Right? You understand? It all depends on the company you're working at. But above this, then it's no longer company, it's, right, just about all plants are going there. So this is where they said, well, we need to establish a standard because I've got a push button, a push button's going to be rated at a voltage, but a 120 volt push button would work great. I mean, it would work great on 24 volts. What changed is when we started adding all this electronic stuff, all these electronic sensors, these position sensors, and these optical sensors, and these laser sensors. These guys have to work on a DC voltage. So instead of just going out there, basically PLCs themselves has established 24 volt DC as being the standard DC voltage. So now I can buy sensors that are set up for 24 volts. Does that make sense? Good question. So 24 volts is the standard. I haven't seen a PLC in a long time. If it runs off DC, they did not use 24 volts. First of all, it's below what? 50. And it also establishes a standard that an electronic company that makes sensors can use to make these electronic sensors. Now the 1100s, we got to be careful with it because they use what? And that's why some of y'all, when I came over there and you had the cover open, what's one of the first things I did? I unplugged it, right? So as long as the cover's closed, and that would be about the only time, that will be the only time in this class where you're going to deal with the outputs on the 1000. So just leave the cover closed on it.
That little snake in the circle,
That indicates it's AC.
but it don't tell you whether it's voltage. It just tells you.
Well, this don't tell you the volts either.
Oh, it's always written on
I'm always usually right. I hear what Jerry said. You hear what Jerry said? He said always usually. That sounds like something I'd say. Okay, guys, y'all go ahead and take a break. Y'all let me go by the break. Now, this is this is the book, this is the symbol that the guy uses for a motor, so that's why I took for granted it was a coil. Yeah, but we already looked at that, right? A PLC execution flow on each rung is from left to right, from the top rung to the bottom rung, moving through the entire PLC ladder diagram. Operational scan rate, the time required to execute the PLC ladder diagram once. We call this the scan time. And we can access this to the status register so I can show y'all where we do this. It shows how long it takes the PLC to scan through your program one time. Well, you can try some tricks because we had big problems when we first started using these things because the CPUs wasn't that fast. And you'd get extremely long programs and that dang thing would miss inputs. Because you pressed a button and it wasn't it was scanning up here instead of it wasn't down to your own. It would literally miss inputs. So we had to do tricks. We had to do little things that we'll talk about a little bit if you take the PLC2 class. But now we usually don't have to worry about that. Why? Because the processors are really fast now. They're really fast. And they're real simple too, guys. They're not like these monsters that they put inside a laptop. They don't have to be because they don't have to multitask. They don't have to run multi-threaded programs. You know, all they're dealing with is just binary. They're not translating anything. It's being translated when you compile it over and send it to your PLC. So that means the CPUs can be really fast and they can be really efficient. So we usually don't have that problem. And then they added things called interrupts that we'll talk about in PLC2, where you can make that push button generate what we call an interrupt, and it don't matter where it's in the scan cycle, it'll go out and take care of it. So that means we can take extremely important input devices and we can make it generate an interrupt. So a scan would be like me, you know, starting with Gary and going back and forth, saying, do you have anything for me? Do you have anything for me? An interrupt would be, I'm up here talking, I'm still doing a scan, but you need to get my attention, and you do what? That's what computers allow us to do. So now you can assign extremely high priority inputs to these interrupts. Scanning from the instruction in the upper left corner, so upper left corner down, right? So it goes looks at the input, runs it through the PLC logic, updates the output. Actually, it updates the tables. PEs, are you okay there? These are output connections to an output device. Output latch, we have the ability, and we'll show this too, where we can actually latch an output on, and then we can leave it on until it'll stay on until we unlatch, which is a really neat instruction. That's really simplified what we can do. One shots, we won't look at one shots in this class. We'll look at it, take PLC2, we'll talk about one shot instruction. And also, Ars Logics use the one shot inside their Allen Bradley programs that run the Festo line in the PLC3 class, which you can take after this one. We'll teach you about one shots too, because they're inside that program. So this creates one shot per scan, and it'll go true, and then it'll go false until the next scan. They have reasons for them. One shot. We used to use them to create a certain timed pulse every time it would be activated. So you get one pulse, but you didn't want it to stay true. I know. Hard to explain. I know.
That's okay.
Yeah.
I've learned enough.
So the processor input scans, processor reads input ports and updates its input status table. Program executes the logic inside of the program. Then it does what? Then it outputs it to the output data table, which is not, and then it outputs it to the actual. Are we okay? Input output addresses are updated. Sometimes specified input and output may be updated in time. We're not going to talk about this. This is the mask. This is the interrupts, and we don't need to. This is basically a scan. So start scanning and rung, the top rung, scans it, updates inputs, does the logic, updates outputs, goes to the next run, next run, next run, sees the end instruction, what does that tell us to do? Yeah, go back up to the first one. By the way, on your newer PLCs, this end is not there because it's understood. I mean, why put something there when you don't have to do that, right? So your newer PLC, especially Large Logic 5000, the end instruction is not there, it's understood. It is there, but you don't see it anymore. So this is our project tree. Everybody understand where the project tree is at? We talked about this several times. Where's the project tree at? Yeah, right here, right? Okay, that's the project tree. So we got some things. We got some stuff about our controller. Then this is where we're going to start with right here. System 0, System 1, and Ladder 2. Most of you cannot do anything with System 0 and System 1. So most of your PLC just leave that off. They don't display it. It's there, but they don't show it because there's no reason to show it if you can't do what? If you can't change it, right?
That's 0 and 1.
Yeah, System 0, and that's what your book says. It says this is where the operating system is kept at. This is what the PLC uses. They don't want you to get into it. They don't want you to change it. So really, it's like the end instruction. Why display the end instruction when you can't do what? You can't change anything. You can't put anything. So newer versions of the RS Logic programs, the 5000, don't show the end instruction. Or the rung with end instruction. So what does the book cover first in the project tree? Huh? If you're looking at the book. What's that? Data files? Is data files next?
Well, it's just listed for.
I'm talking about the book. I'm talking about the book. I'm not talking about the PowerPoint.
Database, they got file, they have data file.
Okay, so this is our first program file. It's called they call it Ladder 2. And notice it comes down here and calls it what? File 2. Okay. You can't change the Ladder 2, but you can right click on it and you can rename it, and I could call it Rich. And notice the tab changed, but it's still considered to be what? Ladder 2. So this is real good because now you can give tabs to, we can create other modules that's part of the program. We call them subroutines. We found out a long time ago that if we wrote these big complicated programs, hundreds of rungs, we're going to do, our rungs maybe have 4 or 5 rungs, that's it. But you get out in industry, you're looking at these things, some of these PLC guys, they might have 500-600 rungs, and you're trying to figure out what section of the program controls this. Well, instead of trying to do that, why don't you just create a program module that handles that? So now instead of you trying to find it in the program, you can just go to the what? To the module that handles that. So I can come over here under program files, and I can type in new. I can give it a name. It's number 3. I give it a name. Notice it pops down here. That's Raymond, right? If I want to see that module, I can come up here and double click on it. and then it adds another tab. So now this is that module right there. So what we have the ability to do is what? Split large programs up into what? Smaller, manageable modules. And we have an instruction called jump subroutine that will cover in what?
Similar to Excel.
Oh, well, similar just about a lot of different things, but here we call these other tabs, but the tabs pop up like Excel. Are we okay there? Okay. And by the way, we can come up here and we can remove the tab, but it's still over here. So, you know, you might have 15, 20 tabs under there. You don't have to display all of them. You could basically maybe display only the one module that you're working with. To get the module to come back up, you just come up here and do what? Yeah, just double click on it and the module tab will pop back up. The only problem you have is the module tabs pop up in the order that you click on them. So they might not be in the same order as they are over here. Okay, so that's our program files. Anything else? What's next? So here's our data files. We have our output data table. This shows us the state of the outputs. It's shown in words. So this would be 0, this would be output : 0.0. So this is saying word 0. And this would be bit 1. This would be bit 0 inside word 1. Okay? I'm sorry, this would be bit 0 inside word 0. Are we okay? Everybody okay? We can display it in binary, which makes more sense. We could display it in octal, or we could display it in decimal, which wouldn't make any sense at all. Or we could display it in hexadecimal, or we could display it in ASCII if it was an ASCII code, if we were communicating with a display. Okay? This is our input data file. So this shows us the state of our inputs. And nothing happens. Let's go online. So if you're not online, this don't mean anything. It's not gonna let me. It's gonna make me create a new program. All right. So now we'll come over here, and this is a program I've already downloaded, but I'll show y'all that. And so I come over and flip these switches. I moved 0 by way over here when I was showing you that. Notice another thing that RSLogic 500 doesn't do. When you upload it from the PLC, it does not give you your symbols. So what they do on this PLC, for 500, even if you set up all those symbols, if you upload it, if you go to a PLC and you upload the program into the application, it don't have the symbols. They've changed that. These tag-based PLCs, the actual tags are actually saved with the program inside the PLC. So if you upload a program from the new application, you get your tag back. But let's see, I'm going to go over here and I'm going to bring up my outputs. I'm going to bring up my inputs. And you notice when I flip my switches, the bit associated with that, can y'all see that? I know this is little, guys. I can't do much about it. I can zoom in, but oh yeah. Okay. We'll move over here to the bits I'm using. Can y'all see it? Okay, here's bit 1. Makes sense. And of course, what do I need to do to cause this output to go true? I got to turn on 0, 1, and 2, and the output goes true. And you notice the output data file, also this bottom one, they both went to what? 1. Okay? Okay, now next, in the list is the status file. So this shows us the status of the processor while it's running this application. One thing it gives us over here on this tab right here, it gives us the what? Gives us the error codes, right? Does it make sense? Another thing it gives us is the scan time. Can y'all see this? So this takes it about 23 microseconds to scan this program. And then it gets us some neat stuff. First, it gives us this free running clock right here. Well, it's not free running; it's actually running off the clocks that's on the PLC. And I'll show y'all later on how you can address these. Shows us pretty good information. Math instructions. We're not going to deal with math instructions over here, but overflows. If we have any overflows, 0-bit, sign bit. If we had a carry, we're going to get a math instruction. Okay, then what's next? Binary time, B3s. We'll go right down the line. B3s, we call these bit files. We can use these for some advanced instruction or shift left, shift right, and sequencer instructions use this. Which we're not going to do in this class. That's advanced instruction. We're going to use them primarily for what we call internal calls. So the only time we've only got a limited number of outputs. Y'all understand that? Okay. A lot of times we want to have a relay whose contacts are always inside the control circuit. They never leave the control circuit. So input 0/4. And then what over here, I'm going to come up here and I'm going to bring down a coil. I've already got a coil. And I'm going to call it B3 code 0/0. So this is not generating an output. So I'm not using one of my outputs. We call this an internal coil. Of course, I didn't give it a symbol. What I can do is I can drag a contact down here. And then I can assign this to CR. What's the next thing I'll probably need to do? Check for errors, right? Click on this guy right here. It says it's what? It says it's clean, right? Now, don't mean the program's right. It just means there's no syntax error. Syntax error is the correct way of writing in a language. So if you used input 5 instead of input 4, it's going to check it and it's going to be in the right syntax, but the program's not going to work right. So it don't mean the program's going to work right. It's just that it's not going to have any syntax. This checks to see if it'll compile over okay. So that we're okay there. So normally I use this one because it checks two things for me. Then we'll do what? Download it. We're going to have to give it a name. Probably need to fix a place to, by the way, most of the time when you try to save on your drive C, the actual, just to drive C and not specifying another location, it's going to tell you it's going to tell you that you don't have the rights. So what we'll do is we'll come up here and choose where we want to put it. So this would be, if you're going to take your programs home with you, right, or keep them, then this is where you'll put your thumb drive in there and you'll point this to your thumb drive, right? Normally what we do on here is if you're not going to use your thumb drive, we'll point it to the desktop, and that way at the end of the semester, it's real easy to find them and delete them. So this will be desktop. I'm going to go out here. I'm going to put it in the folder for this class. Now this tells us that the CPU don't have a name. It don't mean that your program don't have a name. It means your CPU don't have a name. You can name that too, guys. And it's going to switch back into it for us. What? And we're going to go online. So this is a B3 file, which means what? And it don't generate an output. So we'll use a lot of these. I mean, a lot of these. I'll show y'all, as we progress, I'll show y'all some of the programs that actually runs the Festo line. So this is a simulated contact that belongs to that relay, right? You see that? Make sense? Timers. We use timers quite often. Give me some examples of timers. Y'all got a ton of timers on your car. Most cars, we leave our lights on all the time. We don't turn them off anymore. We leave them on auto mode. And you get out of the car, you close the door, whatever, turn it off. Right? But my car, when I close the door, the dome lights stay on for a little while. Then they'll do what? They'll time off, right? You got windshield wipers that you can set at different time delays between what? Between swipes. So timers are all used all over the place. So this is where we put our timers. We establish our timers. So all your timers are going to start off at default. And we'll show y'all as we go along how to set these up. So I go over here, timer, I would say a certain type of timer, I would pull it down. Oops, try to anyway. And then later on, one thing we're going to do is set the time and stuff like that, right? And notice it started what? I'm sorry, we'll give it an address. So we have to give it an address. It's going to start off D4 : and then we give it a timer number. That makes sense? By the way, go ahead.
What time for the close and open the contact?
Well, it controls contacts, and as we get to this, we'll show you how to specify the contacts. That's a good question. So it controls contacts, and we'll show you how to get to them and how to use them when we get there. All we're doing now is just showing you these different levels and what these time run. And we'll talk about the limits for RS Logic 500. We could also come in and counters. Companies always like to count things, right? They have to know that. So here's our counter file, counters. So counters, they're in the same section. Here's a counter. Oops. Oh, I got to go off. I am offline. Oh, I got to specify a rung. Sorry. So there's a counter. This is an up counter. We got two types of counters. Which way can we count? Up and down, yeah. So the counter, we have to give it an address, and so these are going to start off C5 : and then we'll put a counter number out there. So right now I'm using counters. And then when we get to it, we'll talk about how to address, so we can tell when the counter's finished counting, when it's doing this kind of stuff, while it's counting. We'll get to Then we have a control register, which you're not going to be using this semester. This guy is used for instructions that allows us to shift information around, to sequence information. It's really, really neat, but we don't have time in this class to do this. But this is where it sets up the status of what's going on by specialized instructions. We'll get into those instructions if you take the advanced PLC class. But that's where its control register would be. Then we got integers. What's an integer? It's a whole number. Yeah, and we'll look at that. I'll get back to the slides and explain that. But an integer is it's a signed number without a fraction. And RS Logic's calls real numbers. They call them floating point numbers, and these are the F8 registers. These are the big numbers. These are the guys where the decimal point can be anywhere within the number. This guy, when it hits a certain range, it's going to what does your calculator do when it exceeds its range? Well, it jumps into scientific notation. So floating point numbers, this is going to do, as soon as you exceed the range of what it can represent as a fractional number, it'll automatically switch into scientific notation. So it's kind of like your calculator. Most of your newer PLCs don't call these floating point numbers, they call them real numbers. And that's what a real number is, right? Are we okay? And that's everything in the project tree except these guys down here. This is where we can actually force bits. So notice I force bit 4 what? On, and I'm not doing what? I'm not flipping a switch. So right now, I forced it on, right? You understand? So if I was online, then it would go true. Then I could come up here and double click on this and I can hit delete, and then it'll take it back, it'll turn back into a dot. So this is where we can force inputs and we can force out. Now guys, out in the plant, you need to be extremely careful about that, because what you've done is you've taken out all the safety features built into that program. All those sensors that sensing when people's there, it's everything's in the right place at the right time. You can tear up equipment with this and you can kill people.
Why is it there?
Because it's a method of troubleshooting. Number one, it allows us to check a program with a PLC sitting over here by itself. So I don't even have it out in the plant yet, but I know input 1 is hooked up to this sensor and I want this to happen. So what I can do is I can bring this up and I can simulate these inputs without having any inputs wired. So you can actually check your programs out without even having the PLC wired up yet. So it's a really, really neat feature. Or we can see if this output is doing what it's supposed to without going through all the logic to generate the output. So it's a real valuable tool, but what I'm saying is you need to do what? Make sure it's safe. Make sure you're not going to bring a robot and bring something in, bring a clamp down on something that's not supposed to be clamped at this time, right? Because you could tear things up. You could tear equipment up with them, and you could also kill people. Well, what you can do is you can password protect the actual CPU.
I kind of say it's kind of like leaving a key in that.
Yeah, that's exactly right.
Everybody don't have access.
Yeah, the access, and most of your PLCs, we just don't put them out there. For one thing, you've got to have a computer that's got the application on it. So you can't go out there with your smartphone and connect to it. You'd have to have the computer with the application installed on it. In most companies, they should password protect the CPU. So if they password protect it, then you can't do it anyway. And then a lot of your PLCs have switches on them. And you have a run, you pull the switch out, you can't put it in program mode. And a lot of that's these little old ones like this though don't have that feature because, well, no, this is a real PLC. You might run into a 1100. This is the trainer. This is a industrial grade program controller that's mounted as a trainer. So these right here, you'll see. I mean, we got Lehigh Cement is buying a bunch of little 1200s to do some stuff out there with. So there's the data files. Y'all got any questions? Hammond's example. By the way, note that an examine if open instruction is not normally used for a normally closed stop button. And we explain that why.
Keep going,
Yeah, if the wire breaks, yeah, because it's true when it's open. System files, we looked at that. We don't have it. We can't get to these. These are internal registers inside the processor. We can't get to that. And why they even display it, I have no idea. Ladder 2, everybody okay with ladder 2? Holds main PLC logic program, maybe more than one program file that's included that can come in and we can add that. And this is for things that's called subroutine. And where are they covered at? The next in advanced PLC. Maybe several in addition to the main program file called on or accessed from the main program file using what we call a jump subroutine instruction. Selecting a main program file or a routine shows you how to do that in the project tree, right? So you're not going to do that. You're not going to make it. You're not going to make files this time. We talked a little bit about the B3. Now, what they've done as the PLCs have evolved, they've added more memory, which means we might have a timer file, but we're going to be limited to the number of timers we can have. Currently, RSLogic 500 uses 1 byte, 8 bits. So how many timers could we have with 8 bits? How do you calculate the number of combinations? Yeah, so it'd be 2 to the 8 because it's 8 bits. So that means we could have 256 timers. So when you look at the, if you're using 11,000, I mean the 1,000, that's it. That's all you got. If you're using the 1100, we could use some more memory and we could add more timer files. We can add more status files. We might have a T5, a T7. So we can add more files on some of your PLCs if you run out of the 256 that's available. So data files holds the binary state of the inputs outputs. So this is the difference right here, an examine if closed. So if a voltage comes in on the input port, it puts a 1 in the input data file for that bit. If a 0 or no voltage comes in, it puts a 0 in the data, in the bit that belongs to that. So what the difference is the examine if open and examine if closed, the program looks at the state of that bit at 2 different things. So if you're using the examine if closed instruction, which is and this only deals with inputs, guys, switches. This don't deal with contacts used inside the program. This deals with nothing but if you're inputting off an input port. So this is the symbol for an examine if closed. So by default, it's false, right? You understand. And when you push the button, it becomes true. This is the symbol for examine if open. So this is false when the switch is open. Okay, understand. So this is what the program does. If you use an examine if closed, if a 1 is in that bit inside the data file, it says it's true. If you're using the examine if open, if there's a 0 in the bit for the data file, it seizes that true. And this only applies to physical input devices.
So last week we had the diagram up there with the push button normally closed.
No, that's a normally closed push button.
Yeah, but then right next to it we had the normally open. And but it says the examine if open. And somehow you have to set it messed all of it. That's okay, go ahead. You don't remember
You
what.
tell it's true by flipping these switches over there, right? I understand.
Examine if.
Go. I'm listening. So if I was to come over here,
I wasn't listening. It was on the seal insert. The first one on the seal insert.
well, I'm gonna come over here and I'm gonna change this. I'm gonna come up here and edit symbol, right? No. Edit. Got me confused now here.
Wrong question.
No, you asked a good question because we did it the other day. So how do I edit the,
Well, we had two push buttons in the same. And we had
I'm sorry, change instruction type. And right now it's set up for a what? Can y'all see that? Some of y'all sitting in the back. So I'm going to change it to an examine if open. Okay, right there. And then I'm going to check for errors.
My bad.
I'll download it.
Reason I'm trying to get that straight is because I know I'm gonna have to add it.
Probably not. We took a break last time at 49. So what time is it? We got 2 minutes. We're going to try to. We got to get through with this before we go loud. Period, right? Okay, so we're looking at switch 4. Okay, so I've got an examine if open. So right now it's let me switch down here. So now switch 4 is a 0, but it says it's what? It says it's true. Okay, see that? Okay, now I'm going to close it, and now it went to what? It went to a 1, but it says it's what? It's false. Y'all understand that? Okay. So that means if I use a stop button, if I wanted to stop this thing and I use an examine if closed, then what would I have to do? The switch would have to be open for that to be true. Right? You understand? But a normally closed push button, which is what's required. So I would have to use a normally open push button for a stop button for it to work. What's the problem with using a normally open push button with a stop circuit? If a wire breaks, you can't do what? You can't stop it.
So somehow you put on there it needs to be true. When the examine went closed.
But I'm not using an examine if closed. I'm using an examine if open. So and that's why I'm trying to get y'all away from calling that a normally closed contact and calling it an examine if open when we're dealing with an input device. Now, if we got those contacts down inside this, it don't make any difference. It's only when you're dealing with an input device that you have to know the difference between an examine if open and an examine if closed.
Well, I've got here examine if closed, if it's a normal closed.
That's wrong. An examine is closed means,
Examine if open, I'm sorry.
Thank
Examine if open.
it says that's what we need to use, but it depends on your application, right? You can use any symbol you want to, but if you're using a stop button, you better use an examine if closed and not a what? An examine if open. Up to that, after that, it's up to you, as long as you understand the logic and you understand the difference between an examine if open and examine if closed. So right now it says that contact is true, but when I look at the bit file, it says what? 0. So what does a 0 mean? A 1 mean? It means what you make it mean inside the program, right? You understand? So when I come up here and close that switch, see, it went to a 1, so the bit goes to a 1 if it sees voltage. It goes to a 0 when it don't see a voltage. It's up to you to decide what you need to do or how you need to do that, right? You understand? So an examine if closed works the way our brain works. An examine if open does what? Yeah, opposite. And that's where it gets people in trouble. In this book, this author uses that symbol for a stop button, which tells you right off the bat what? He's a programmer and not people that has to work with certain. Of course, I've written books before, and I understand there's so much stuff you've got to know and got to think about that I can understand. I have more slack with books now than I used to, but yeah. Now, what's the range? If I'm using a 16-bit number, how many numbers could I represent? Which is what? 65,536, right? How did you get that? Just take the base and raise it to the number of what bits. Why are we limited between 32,700, which is half of it, 32,738? Wait, by one of those got to be wrong. What's one half of this? What's one half of 65,536? So I'll update this. You should have one more negative number than you have positive. Computers use something called tooth complement, which I'm not going to explain. But what they do is they have to represent a signed number in binary. So what they do is they sacrifice the most significant bit as the sign. If it's a 1, the number is negative. If it's a 0, the number is positive. If we sacrifice one bit, that gives us exactly half the combination because I sacrificed bit 15, right? Right? You understand that? Now, why do we have one more negative combination than we have positive combination? Did somebody figure that out? Good. 0 has no sign. Good. That's smart. Yeah, good. So what they do is they sacrifice the most significant bit as the sign bit. If they do that, that gives us half the combinations, and we get one more negative combination than we do positive. If we're using long words, we can get way up there, but notice we still have what? One more negative than we do positive. So a long word is 32. Good. Floating point. These guys are used. So it's a 32-bit number. Couple of bits. The most significant bit is the what? Sign bit. Then bit 0 through 22. This would hold the exponent, and then the other bit would hold the zero, which is the significant number. We using floating point numbers. We can get all the way up to 3.4, up to 10 to the 38, up to 10 to the 38. So we can get way up there with these guys. But as soon as you shift into scientific notation, then the number's not as accurate, right? Understand? That's when you start rounding. Just like your calculator. Are we okay? Big number. You need to know this layout? No. You just need to understand, right? Understand. Thank you. B3s, we're going to use these primarily as internal relay coils. What's an internal relay coil? These are decision-making coils that do not have to sacrifice one of our output cords. For some reason, PLC programmers think you got to assign everything to an output cord. You don't. You can use these internal coils, right? In motor controls, we call them control relays. These are little old tiny relays. They have a bunch of contacts on them. But these are relays whose contacts never go into the power circuit. So B3, some PLCs allows us to assign more. The 1100, we can have more than one B3 file. Well, not a B3. We can have a B10. We can have a B8. If you're working with the 1000, 1000 is a fixed PLC, guys, and you get a fixed PLC, you get what you buy, right? You understand that? Are we okay? Of course, y'all need to know the number. So up to 256, right? 0 to 55. It is. Let's take a break. 10 minutes. So y'all okay on the B files? By default, you get a B3. But like I said, some PLCs allow you to, you got a B3 file and you can go from 0 to 55. By the way, I got a timer on my watch and I set it for 10 minutes here. So we'll start up, guys. We got another instruction that we need to look at a little bit. These are called latch and unlatch. And we use these a lot because they save us some circuitry and also they scan things. So notice we, up in run 0, we're using an input switch. And this says latch B30, so this is an internal relay. Once we've latched, then the input can go false and the output will stay true until we do what? Not force it. We're not. So down here we got the same coil address, but here we're using an unlatch instruction. Up there we're using a latch instruction. So what I've done is I've stuck this into our program so I can show y'all this. I'm using an actual output where the book uses a. So here it is right here. I've added comments. So here I'm using output 4, output 0/4. And down here I'm using output 0/4, but this is a latch instruction and this is a what? Unlatch. So it's already uploaded, so I'm gonna go online. And then I'm gonna come up here and just flip the switch. I'm gonna use the momentary contact feature. And notice now output 4 is what? It's true. Well, this over here is not true, but what did I tell it to do? I told it to latch it, right? Okay, and how long would it stay latched? Until you unlatch it. Till you unlatch it. So latch, unlatch, latch, latch. So notice I'm using a momentary contact. Of course, once it's latched, you can't latch it anymore. So this switch over here could go true 1,000 times and it's not going to change the state because it's latched, right? And then when I'm ready for whatever it's controlling to go false, then I use the circuit that has the unlatched circuit. And we use this a lot. These are the actual programs that controls the Festo line over there. We're going to get a chance to go over and look at it. You see, there's our first, they're using a watch there. Can y'all see that? Latch. And then they're using the unlatch. This is, let me show y'all this subroutine. This is where they're basically trying to figure out things, if everything's in the right position, but they latch, they unlatch, they latch, they latch, they unlatch, they latch, they latch, depending on the sequence. And look how many are they using just this module right here. And they're not even generating outputs. All they're doing is just making decisions on when to generate outputs. So these guys scan faster than a 3-wire control or a memory, and they're a lot simpler. Are we okay? So if you take the PLC3 course, you'll be converting these programs over to S7, Siemens S7 program. Yeah, what we do in we call it PLC3. It's actually called ILT212, and it's automated PLCs and automated systems. And what we do in that class is when we bought the Festo line, it was installed with Allen Bradley PLCs. And what we do in that class is we convert the line over to Siemens PLC.
So it's in the PLC on that also.
Well, what we do at the end of the semester is we convert it back to Allen Bradley. Well, we don't actually convert it back to Allen Bradley. We just pull the mount out and put. So we use these mounts. That's the reason why we bought these mounts. So you put the S7, the 1200 on this guy. You wire it up. You take that program, convert it over. You go over there, plug it in, and hopefully it works. But at the end of the semester, what we do is pull these guys out and take the Allen Bradley and stick it right back in there and plug it back up.
I thought it was enormous.
It is.
Even that.
And y'all can take PLC3, by the way, if you want an introduction to the Siemens PLCs. As part of the electives down in your degree plan, you can take that after you get through with this class.
Take PLC2 or
Yeah. Well, you can take 2 and 3 if you want to. But you don't have to have 2 before you take 3. So the PLC has 3 modes. What's the 3 modes? We can put it in program mode. This is where we can download or upload the program. We can put it in run mode. This is when it actually switches and runs the program in current memory. We can put it in remote mode. This is where you switch it between the modes with the application. So all our PLCs are fixed PLC, or not fixed, but they don't have this switch. But if you look at this one, here's the key switch right here. That's run, that's remote, and that's program. So if we put it in remote, then we can switch it with the application between the other 2 nodes. If we put it in run and pull the key out, then people can't do what? They can't program it. They literally have to have the key. Unfortunately, the key is exactly the same for all the CPUs. So that means there might be a lot of keys out there, right? You probably can. Our programming application has 2 modes. We have the offline mode. This is when we create or modify programs. And then the online mode, this is where we can upload or download the program to the PLC. We can upload it from the PLC, or we can also monitor on the online mode. And you do this. So this is where you switch your application. You switch it on the application itself. So right up here. So we can switch it between the what mode. We can go offline. What can I do with offline? Yeah, modify the program or create it. After we check it, right? And that's what's nice about the trainer. You can screw up on your trainer and not kill people. But you do hopefully know that it's not working right. Then we can do what? We can download it from here, but normally, we can also switch it to program mode from here. Okay? But normally when you upload a program, what's nice about this application, it asks you see all these boxes pop up there, it asks you, do you want to switch between those modes? So let's re-download it and watch us switch the application. Oops. Every time you download a new program, they want you to give it a version number, but you don't have to. And then it says, okay, do you want to download? And I'm going to say what? Yes. The processor's in the run mode. Do you want to switch the mode? You never do this if you're in the remote mode, right? It says, do we want to switch it to the program mode? I'm going to answer what? Yes. Then it says, okay, do you want to change back to the run mode? And I'm going to say what? Do you want to go online? So now it's going to switch the application online so we can do what? So we can actually monitor the program. Siemens application does not switch to the monitor mode automatically. You have to specify that. But that's basically about the only difference. Instead of using, and I'll try to show you all a little bit, instead of using this menu, it uses icons up on the bar for download, upload, and that kind of stuff. So everybody okay on downloading? Not very hard, right? I understand. But normally we check it first. Like I said, I like to compile it and check it because I do 2 things. But remember, when you check it, it don't mean the program's right. It just means there's no syntax errors, right? Everybody understand that? Well, I can tell you I heard that. Well, I checked it before I downloaded it. But the program itself was in the right syntax, but it was what? They used the wrong inputs or used the wrong thing. It's like a while ago when I was by habit, by going different addresses. When I first entered this, I used a different address. I used output 5, and then but it compiled over fine and uploaded fine. But when I got it up there, I could latch it, but I couldn't unlatch it because I gave it a different address, right? So. Note that these conditions are only true for a modular SLC 500 PLC with a 120 volt DC input module with an unspecified output module. This is not the wiring method used with the PLCs in the lab. So that's what we need to look at. So what you're going to do on your lab book, they're going to show you this. You've got to mark that garbage out of there because that's not our PLC. Everybody okay? So you'll just start out by just drawing over them. So this is what we've got, right? You understand? So we have to establish a common. What's our inputs? Our inputs on both our PLCs that we're going to be using is syncing. So what does that mean? Yeah, but what does syncing mean when I draw my... So I'm going to put my DC voltage source up here. And I'm going to point the minus toward the common. Right? Understand? And then I'm going to come over here and run a rail down here. And then I'm going to do what? Then I'm going to connect my inputs over here. Now ours is using, and we're using a sourcing output, and then we'll connect our output devices over here. Okay? Yes, no?
Yes.
But when you look at your lab book, it's going to tell you to draw the wiring diagram of your PLC. But the problem is this is what they're going to put up there. This is in your lab book. And it's what?
Wrong.
Yeah, it's wrong. I can spell wrong. It's wrong. So we're not, but all you're going to do is you're just going to come up here and do what? Mark that out. And then over here, you're just going to draw the battery depending on which direction your PLC uses. Now, the symbol does not have that line through it. I had people draw the line on test. Draw this line going through it. It's just that's the way it is on ours, right? And then if I'm using the 1000, I'm going to draw a circle over here and put this. That means what? AC. So on AC, there's no such thing as syncing and sourcing. The only time syncing and sourcing comes into play is when you're dealing with DC. And in newer PLCs, they're going to use a lot of DC. For one thing, they don't have to deal with AC, and DC is easier to control. And so a DC output module is easier to control than an AC output. We can do more things with it. And then plus, it's 24 volts, which means it's below what 70E considers to be what? Lethal. So on the 1100s, you'll just draw it like what? Just draw it through the line, just like that. And of course, what are our batteries? Our DCs are 24 volt. But putting that up there is, and odds are that won't be a motor. Odds are it'll be a relay that controls the motor. Are we okay? So y'all just modify y'all's lab books a little bit according to whichever PLC that you're on. Are we okay? Run mode, are we okay here? Offline, online. So offline, what can we do?
Program.
We create the program, we modify the program, right? Online, what can we do?
Run the program.
We can download the program or upload a program that's already in the PLC. We can also monitor the program if the PLC is in the run. Are we okay there? Forts, we've looked at forts. Everybody okay there? So these are the conditions. So you got to be in the run mode to force. Force has got to be enabled. And then down here in your project tree, don't use this output up here. You need to come down here and find the folder that's in the force. Click on that. It'll pop up a bunch of dots. You can double click on the dot and put a 1 there. Then if it becomes true or false depending on whether you're using it on the input. It's depending on whether you're using examiner open or examiner closed. But your output will always energize. All right? Everybody okay there? How do you get it back? Well, you just highlight it and hit the delete key, and it'll go back to a dot. And this is showing that. Double click on the input output, right? Double click on the input or output to force, enter 1 or 0. Delete to do what? Turn to normal. So every PLC I've done with, I've played around with, gives you this ability. Siemens and 5000 is a little different. You have to actually set up force tables, so they're not there for you. You have to set up a force table and decide which inputs you want to force and which inputs you want to, outputs you want to force. So they're trying to control that a little better. Even though the force is a powerful tool troubleshooting using the force instruction, an industrial plant has the potential of causing fatal accidents. And I should add some more tearing of the equipment. You could bring big clamps down on something and squash it, and you can swing something around and wipe stuff out with it. I think I told you about me forcing a relay and bringing down a side clamp, right? Did I tell you that story? Luckily, the strip they were running that day was too small and the clamp didn't grab the strip. But so what's going to happen, I don't know if you'll notice it. So how do you can look at it and tell if you're in the run mode. Yeah, see that little guy right there? Yeah, so that means this guy is in the run mode. Two vertical rails will be spinning. And we're not going to talk about printing. So we're through this, what we're going to talk about on this chapter and what's going to be on the test, which is coming up next week, right? I don't know.
I think it's Monday.
Tuesday or Thursday.